Video is on exponential functions, and these are functions which are written in the form f of x equals k times a to the x. So we'll start off with an example f of x equals 2 to the x. Now you might say, well, where's the k in this case? Well, if there's no apparent k, that means the k value is 1. And the values of k and a have an impact on the appearance of the function when it's graphed. So in this case, k is equal to 1, and the k value informs us of a couple of different things. It directly informs us of the y-intercept. So whatever the k value is, that's the y-intercept. And I would just like to add the proviso here that I'm basing this on the function being written in the form k times a to the x. I'm not considering a constant being added on at the end of the function. That would obviously have an effect on the function overall. Whether k is positive or negative also has an impact on the diagram. K being positive indicates that our function is going to always be positive. This means that the function would always be above the x-axis. K being negative indicates that our function is negative, which means that the function would occur entirely below the x-axis. Here I have an a value of greater than 1. In the simplest scenarios for exponential functions, where the k value is positive, then an a value of greater than 1 indicates that the function is increasing. It is, however, very important to note that if the k value at the start is negative, well then that will reverse this situation. If the k is negative and a is greater than 1, then f of x will be decreasing. So while the a value tends to dictate whether the function is increasing or decreasing, it can be affected by the sign of the k value. Let's take a moment now to graph this function f of x. I want to graph it in the domain -1 up as far as 3, so take a moment to calculate your points for this function in this domain and draw a graph. Pause the video while you're doing that, and then play in a moment and see if you have the correct graph. So here we have the graph of f of x equals 2 to the power of x, or 1 times 2 to the power of x if you like. So let's just see the implications from the k and the a in our function for the actual visual graph itself. So looking at our k value is 1. That determines our y-intercept. If we look at the diagram, we can see that our y-intercept is in fact at 1. Because k is positive and a is greater than 1, we can see that our function is increasing, which just means that it's sloping up. And it's always sloping up the whole way along the function. Notice as well that because k is positive, the function is entirely positive. This means that the function is always above the x-axis. It is only in the positive region of the graph. It's important to note also that in a function like this in the form k times a to the x, that the x-axis is an asymptote of the function. What we mean by this is that the function gets closer as we travel to the left, gets closer and closer and closer to the x-axis, but it will never actually meet it. And it's important that when you're graphing an exponential function that you make this clear. Never run your function into the x-axis. It's always going to hover just above it. Next, let's have a look at the function g of x equals -2 times 3 to the x. And we'll make a few observations about the function in its written form before we go to look at its graph and see what the links are. So first of all, we note that the k value in this case is -2. So I'm expecting that my function will go through the y-axis at this value. I also note in this case that the k value is negative, so I'm expecting that the function will be entirely negative. So what this means is I'm expecting the function will be below the x-axis. Looking at the a value in this case, I notice that it's greater than 1. Now, if the k value was also positive, I would expect the function will be increasing if a was greater than 1. But this k value is negative, has an impact on the function. So a is greater than 1, that would be a default increasing, but then multiplied by the negative, that means it's decreasing. So I have to pay attention to both values to see what the implication for the diagram will be. I'm going to graph this function in the domain -1 up as far as 2. So again, pause the video here and do that again yourselves, and then play and see if you're correct. So you can see my points here on my graph. And when I join the points together, it results in this curve. So let's just have a look again at the information that we gleaned from the function when it was written and compare it to the diagram. So k was a negative number. So we had, it was -2. So we had our y-intercept, we expected it to be at -2. We look at our diagram, we can see that that's correct. We also notice that because k is a negative number, that we expected our function to be negative, and we can see that in fact it is below the x-axis at all points. We also noted that a was greater than 1. So we said that in the default setting, if we had a positive k, we'd expect our function to be increasing, but the k being negative has a knock-on impact. So we see that f of x is decreasing because that k is less than 0 as well. And you can see when you look at the graph that it is in fact sloping down at all points. Let's just think for a moment. If I was to change this function slightly and make it be just 2 times 3 to the x, how would it look different? Pause the video for a moment, have a think about this, and then play and see if you're correct. Okay, so if I was looking at 2 times 3 to the x, what I would actually be seeing is the reflection of the curve that I've just drawn in the x-axis. So I would have a curve that was increasing and above the x-axis instead. It's like I would just reflect this function above. So this minus here at the start basically has a function where it almost finds the reflection of a function through symmetry in the x-axis. Our next function is h of x, and it is 3 times half to the power of x. So again, let's make our observations about k and a and think about the implications that'll have for the graph. So my k value is 3, so that means I expect the function to go through the y-axis at 3. I also note that because I have a positive k, that my function is greater than 0. It's going to be above the x-axis. This time I note that my a value isn't greater than 1. It's between 0 and 1. And the default setting for this is that it means the function is decreasing. I just have to watch out, is there any interference from the k? The k is positive, so that won't affect it. Okay, so I can say that when a is between 0 and 1, my function is decreasing. This means the function is sloping down. Just before we go to do any graphing, it's important to note that there are alternative ways in which this function can be presented. You can see here that the 2 in the denominator can be written as 2 to the power of 1. So it would also be possible to write this function as 3 times 2 to the minus 1 to the x. This looks a little bit clunky, but I can see that there's a rule that I can apply from my rules of indices, and that is the power to a power rule. So I can multiply these two exponents together, and I could write this function as 3 times 2 to the power of minus x. Probably better written as this 3 and then the 2 in brackets to the power of minus x. Okay, so we're going to graph now. In the domain minus 2 up as far as 3. Pause the video here for a moment while you do this, and then play and check and compare to my graph to see if you're correct. So I've marked my points in, and now I'll join them to make the function. So here's my function, and let's just see then how it compares to our predictions based on the written function. So k was equal to 3. Yeah, that's the y-intercept. I can see that quite clearly in the diagram. The k value is a positive value, so my function is entirely positive. It's always above the x-axis. And again, just notice that the x-axis is an asymptote of the function. The function doesn't actually ever get as far as the x-axis, even though it gets very, very close. Our a value is a proper fraction. It's between 0 and 1. And there's no interference from k because k isn't negative. So my function is decreasing. And you can see that quite clearly here. It's decreasing at all points along the function. It's always sloping down. Even when it appears to kind of flatten off a little bit here, it's still decreasing ever so slightly. Finally, let's graph j of x minus 3 times a half to the power of x. I'm choosing this particular function purposely because of its similarity to h of x. So as we're going through this, just be having a think, how do I think j of x will look in comparison to h of x? So let's start by making some observations. Well, the first observation that I'd like to make is the alternative way in which this function might be written. It could be written as minus 3 times 2 to the power of minus x. Let's have a look so at our k and a values. K in this case is obviously minus 3, and this is the y-intercept. I've got a negative k value, so I expect to have a negative k function. Sorry, I should rephrase that. I have a negative k value, so I should expect to have an entirely negative function, i.e. below the x-axis. A is a proper fraction, i.e. it's between 0 and 1. Now, under normal circumstances, this would indicate to me that the function was always decreasing, but there's interference from this negative in the k, so I reverse that and I end up with a function that is always increasing. Sorry, I've just realised I had a slight error further up the page there. It should say back up here in h of x, if and only if k is positive. My mistake. Okay, so we're going to have a function that is increasing. Right, so now we're going to go and graph this function. We're going to use the same domain as before, minus 2 up as far as 3. Pause the video for a moment while you graph this. And when you have graphed, compare it to the previous function and see what do you notice when you compare the two. So here's my graph of j of x, and let's just have a look and see if our expectations were fulfilled. So we were looking at k equals minus 3 being the y-intercept, and we can see in fact that the function does go through minus 3 on the y-axis. We also expected the function to be entirely negative, so completely below the x-axis because of that k being negative, and we can see that that expectation has also come through. We said that a was between 0 and 1, which would normally mean that we would be decreasing, but that was affected by the k value being negative, so that reversed that situation to mean that f of x was increasing. And we can see that throughout our function is in fact increasing. And I also asked you to think about how h of x and g of x might be related, or what observations we could make about them. So let's look at the two of them together now. So I have them still here as two separate diagrams, and you can see that they look really very symmetrical. I'm actually going to completely overlap their x-axes now. And you can see that the x-axis is actually an axis of symmetry between these two functions. And the only difference between them is the sign on their k value. So h of x having the positive k value is above the x-axis, and j of x having the negative x value is below the x-axis. Both of them have the x-axis as an asymptote, so while they'll both approach it and get very, very close to it, neither of them will ever reach it. Bear in mind that in this video I have not dealt at all with the idea of adding a constant onto the end of the function, so the rules that I've looked at here are purely when the function is in the form k times a to the x. Adding a constant or subtracting a constant from the end of a function will push it up or down relative to the x-axis. We've encountered this when graphing trigonometric functions, but I'm not going to mention it in detail in this video.